next chapter is designing attacks against servers. Chapter objectives. Identify methods of attack against servers. Review methods of covering tracks and hiding information, because once we get on the server, we might want to hide some information there. So the good news is servers are there waiting to be attacked. We love servers. Servers are there to serve. Well, they serve us, the attacker, too. So with a server, we don't have to do anything to get them to come to us. The server just sits there and waits, and it waits until somebody connects to it. That connection could be legitimate, or in the case of a red team hacker, it could be an attacker. And we love it. They just sit there and wait for attack, sitting there with their ports in the listening up position, and they're ready to be attacked. So what are some of the server attacks? Well, in the Windows world, we have the ever wonderful NetBIAS or SMB, server message block. We love it because Windows loves to talk to everybody and tell everybody who it is, which is good for the hacking standpoint. Pilfering, because we can pilfer information just sitting and watching a Windows network. Password cracking, because up until the latest versions of Windows, they had a very weak password algorithm. It's still there in the later versions of Windows, it's just not enabled by default. And remember, these are the servers we probably will see in that DMZ. Exploiting trust. Windows systems trust who they think is on the network is allowed to be on there. Then covering tracks in Windows, because they give us some nice little features, as Microsoft calls them, to be able to hide information. In the Unix Linux world, we look for remote shells and some other form of attack against the server, or if the server is running Samba, that is running SMB for Windows, there's been multiple vulnerabilities in that. And then denial of service, where we can't do anything else. If it's allowed in the scope of work, we're just going to shut the server down. NetBIAS. We love this thing. It's inherently flawed. We always wonder what was Microsoft thinking. Why? Because it allows what we call a null session. It means I can connect to what's called the inter-process communication, the IPC $share, and enumerate information. Finally, after years and years and years of us using this as an attack, Microsoft started giving up less and less with the newer versions of Windows. But the null session is still available. And it can be a way to identify the operating system. When you connect to a null session, you can see, okay, how much information is coming back from this target. If not a whole lot of information is coming back, it's probably one of the new versions of Windows. And we can manually do it with the netuse command, and then do our universal naming convention, / / 192.168.202.33 there in the example. Any IP address could be there, or any NetBIAS name, and then we connect to the IPC $share. Again, that stands for inter-process communication. What we do is we use a null user with a null password, which is why we call it anonymous null user. And the tool we like to use to do this with is called SuperScan, which is free from Foundstone. Well, here's an actual diagram and picture of SuperScan. And it shows you that this host, which is called external DMZ, which it's an external DMZ host probably, and what it's showing us is the remote services on this machine. So we've connected to this anonymous null connection, that IPC, inter-process communication $share, and provided a null user, null password, and this is how much information we got back. So as you look at the diagram here, you see we got quite a bit of information. This is the services running on the machine. We access this over a network without any credentials other than the anonymous null user. In this next example, it's information in the NetBIAS table. So if you go into a Windows machine, you do an NBT stat, you will see the NetBIAS table. That shows you the workstation's name and some of the services that are installed on the workstation itself. In this case, in the diagram, we're showing you that it's got the master browser, and it's been designated the master browser. It's external DMZ, and it's a member of the work group, which means by being a member of the work group, it's never been put on a domain. So it's a standalone server. And there we're showing you, we got the MAC address, which is good to know because we can spoof the MAC address. Remember, in our networks, positions of trust. So if we spoof the MAC address to this external server, it might have more trust with a machine further in the architecture. And then we show the actual null session connection, successful, and then the MAC address, which you just see, we couldn't get the MAC address of that. The workstation, the users, the groups are all empty. That's because coming along, Windows XP, Microsoft stopped giving up this information. But if by chance when you're doing your external testing and you're doing red teaming, you run into an older machine, there's a potential chance you'll get this. But again, the anonymous null connection, you want to test for it because there's information you can glean from that. This is the example of the anonymous null connection against a Windows 2000 machine. As you look at this, look what we used to get from the anonymous null connection. Remember, there's no credentials being entered here. There's nothing being entered here other than that anonymous null user with a null password to the inter-process communication hidden share. And as you see here is we get the entire password policy for this target. So this used to be a really cool feature that as a red team we could get a lot of information on. But Microsoft over the years has made it more difficult. But still we have to test it as a red team. A good red team member will try the structured methodology and look for targets. There's a chance you might have an older target in the picture. So this is on the continuation of this anonymous null connection. Since this is Windows 2000, you see we did get a successful connection. We did get the MAC address. We got the actual MAC address and there's more than one network card on the machine. And we also got the type of workstation it is. In this case, it shows you it's Windows 2000, which is Windows NT version 5.0. And now look at this from NT. Should never run into Windows NT 4.0 anymore. But if you do, look how much information NT gives you. It gives you the password change, password expires, locked out, disabled, number of logons, bad password count, you name it, you've got it when you've got Windows NT. Hopefully you'll never see this in your networks today. But from an attack standpoint, if you do, smile, you've got a present. Pilfering. Now we want to look at cryptography and introduce the landman hash. Grabbing password files, cracking passwords. All right? This is what we do against Windows that enable the weak algorithm. Cryptography. We'll define some cryptography, the types, cracking and what cracking really means to cryptography, and then hashing, which is the one-way function that we use for brute force password attacks. Encryption. It's the process of taking a readable form and scrambling it in such a way it's not readable. Remember, as red team hackers, we don't need to know all the mathematics that goes into encryption. By all means, there's plenty of references for you to know that. We just need to know the basics. And encryption is a two-way process. It means we take plain text or ciphertext and we convert it to ciphertext. So plain text to ciphertext or clear text to ciphertext. And then ciphertext back to plain text again, or ciphertext to clear text again. That's our two-way process. Goes into an encryptor, comes out ciphertext. Goes into a decryptor, comes out plain text. Here's we got some types of encryption. We have a stream cipher and we have a block cipher. In a stream cipher, it encrypts the data as a stream. The key note here is the length of the clear text and the ciphertext are the same. So that means if we take the clear text and the ciphertext, we possibly can get the key because the key length will be a derivative of the clear text and ciphertext. In block ciphers, we encrypt blocks or chunks of data at a time. This is mainly to avoid an actual problem with stream ciphers. The length of the ciphertext is a multiple of the block size. If necessary, we add padding to make the data a multiple of the block size. Most of your ciphers today will be block ciphers. There's not many stream ciphers today. Then we have encryption algorithms. We have a symmetric algorithm and an asymmetric algorithm. And just like it says, symmetric means the same, the keys are the same, and asymmetric means the keys are different. That's where we have our public key and private key in public key cryptography. Crypto cracking. A lot of times a hacker will announce, I cracked this algorithm, I cracked that algorithm. So let's give an analogy here. I created an algorithm and I call it Kevin's algorithm. Well, Kevin's algorithm is determined, has a brute force factor component where I can brute force crack the algorithm, and let's say I'm a pretty good cryptographer, 10 years. That's not very good cryptography, and I'm not a cryptographer by any means. But 10 years is what the brute force component that the researchers figure out is the brute force component for Kevin's algorithm. Now what happens is, say Bob or John or somebody like that goes and they do research and they figure out a way to crack Kevin's algorithm, my algorithm, in 9 years. They can post the fact that they have cracked my algorithm because it's faster than the brute force work factor component. However, it does not mean that data secured with my algorithm is actually compromised. What it means is they found a method faster than brute force. And that's what we're thinking, and it's important to understand when it comes to cryptography and cracks of cryptography. Having said that, any crack in cryptography should be taken serious because it shows a weakness. And once it shows a weakness, the weakness spreads until somebody cracks it fully. A posted crypto hack just means the information found was a method faster than brute force. So what is hashing? Hashing is a one-way process. That means when we hash something, it's infeasible to detect the input from the output. It's usually used in integrity checking. Anytime we modify a file, the message will change, the hash will change. That corresponding hash change identifies the integrity of the file is no longer intact. In fact, it's been compromised. It's been modified. The attack against integrity is modification. Hash functions are used to compute the data before and after transmission. The output results are compared to verify that the data has not changed. This is what you should do every time you download a program or file from the internet. If it has a hash, and most of them do, you should verify the hash before you install or run that program. Hashing is also used in password storage. Data encryption standard, the old DES, was used with Unix. MD5, FreeBSD. LM is our landman hash we've been talking about in the Windows world. NTLM is the Windows NT version of the landman hash. And then Blowfish is the hashing algorithm used by an operating system known as OpenBSD, OpenBSD Unix. Well, what is the landman hash? Well, it's Microsoft's attempt at creating crypto when they created Windows. Unfortunately, Microsoft wasn't that great at cryptography. Didn't work. Made critical errors in the process. Resulted in many of the problems we face for systems and still a challenge today, because even though starting with Server 2003 and above, Windows Vista and above, it's no longer enabled by default. Some organizations will enable it or applications will use it, and you will have the weaknesses of the landman hash, and that's why we cover it here. Because as a red team hacker, if you compromise a machine, you want to go after the password file and try to compromise the passwords. Now here's an illustration of it. If we take a password here, Cardwell, my surname, and first thing Microsoft did with Cardwell, even though it's mixed case, is they convert it to uppercase. What would that just do to the combinations, permutations? It cut it in half. Okay, not good in cryptography. Next they do is they split it into two 7-byte chunks. Okay, the first 7 bytes is Cardwell with one L, and the second 7 bytes is one L with padding. And that's the absolute insult to cryptography, is to pad anything, because that gives you a repetitive pattern. Repetitive patterns are bad in cryptography, good for hacking. So when you look at this, that second 7-byte chunk is only the strength of one character. What about if the password is less than 8 characters? Then what is the 7-byte chunk? The 7-byte chunk in the landman hash is all padding. And that padding begins with a double A and ends with a double E. So that means when you look at it through a password cracking algorithm, which we will actually do in a lab coming up, you will see that the padding always starts with double A and ends with double E. And that is a problem. And there's a diagram to show you the padding in a password cracking tool. So as you look at the red box, you see starts with double A, ends with double E. And the administrator password, according to the tool there that is reflected in the picture, a tool called LCP from Russia, it says less than 8. That means the password is less than 8 characters. Therefore, the padding there in the red box, double A, ends with double E. The amounts in between doesn't matter. Just look for a double A ended with double E, and you know you've got a short password. If you look at the password there for instructor, even though it's not in the red box, can you see it starts with a double A, ends with a double E, and therefore it means it's less than 8 characters. The final thing here talking about this, in Windows, 2 users if they have the same password, do they have the same hash? And the answer is yes, if they use the landman hash or the NTLM hash. Why? Because Windows does not use a salt or a seed. A salt or a seed is a random value used in Unix and Linux, so two users with the same password in Unix and Linux do not have the same hash. So how do we grab the password files? Well, it's what we call the SAM database, the Security Accounts Manager. It contains the password hashes. Active Directory maintains the domain controller hashes, and there's the location on the slide of where that is. Okay? It's hard to move. But the SAM database file is in System32 config. Everybody knows that. So because of that, Microsoft had to protect it. So what they did is they locked it, as you see here in the next slide. It's located system root, System32 config. It's locked by the operating system. But we have tools to get around this lock. We have to have admin to succeed unless physical access is possible. If physical access is possible, we just boot from a device and overwrite the password. PWDump and FGDump. PWDump was the original tool to dump the SAM database and get past the locks. So what happened was Microsoft protected the password file, and the makers of PWDump found a way to crack the protection. FGDump is the latest tool to bypass the lock. All right? These are tools we can use if we do get access, transfer the file onto the machine, which is what we do in a red team environment, and then we can grab the password hash file, and then we can grab it into a password cracker like John the Ripper, who you will see in a lab coming up, or another tool, and we'll crack the password hash. Password cracking. We have multiple types of password cracking we can do. A dictionary, which means we can load a dictionary from any language, and we can take every word, hash it, make a comparison, and look for a crack. We can do a hybrid, which is we take a dictionary and append or post-pend words or letters onto the dictionary words and look for a match. Important note here, there's a dictionary available pretty much for all languages. There's dictionaries available for military terminology, those types of things. And do we have any Star Trek fans out there? There's even a dictionary available for Klingon, the Klingon language. All right, so there's a lot of things out there that the hackers have set up to try to password crack. Brute force is going through every possible combination until you actually crack the password. And then a rainbow attack. A rainbow attack, a guy named Philippe Ochlin. Philippe Ochlin figured out why go through all this time that it takes to go through brute force password hashing cracking. Instead, let's use a pre-computed table. And this pre-computed table has become to be known as a rainbow table. And what a rainbow table is, it's pre-computed hashes already created. So what you do is you load the table that matches the hash that you're looking for. The problem is size. These can be terabytes in size. Do any of you have a terabyte of RAM? If you do, good on you, because it's coming, but I don't have a terabyte of RAM yet. But people will eventually have a terabyte of RAM. The problem is you can't pull a terabyte table or a multi-terabyte table into RAM at one time. So what they've done is they break it up into what we call chains. And each chain has a beginning hash and an ending hash. And what they do is they only pull the chain in that has the corresponding hashes that match the hashes you're trying to crack. There's also numerous crackers online that we can crack hashes. You submit the hash, and within 24 hours you get an email with the cracked hash. These are all good for our red team concept. Right, LoftCrack was the original master tool. Peter Zatko, who now he was working for DARPA. I think somebody said he weren't, and he left and went to Google. But anyway, he's working for one of the big companies now. He was a hacker by trade, a security researcher, test the extremes. He was the one that reverse engineered the original landman hash from Microsoft. Well, what he did is he wrote a famous paper called Weaknesses of the Landman Hash, but he didn't stop there. He wrote a famous tool called LoftCrack. LoftCrack's still available today. Some of you might know it. It's a commercial tool, but if you have a budget for it, it's a great tool, one of the fastest for cracking passwords. LCP, that was the example in the diagram I showed you. As I said, it's from actual, like a LoftCrack, looks like a LoftCrack clone, and it's LCP soft. And then my favorite tool is probably John the Ripper. John the Ripper has a commercial and a free version. What I like about the tool from Solar Designer, he's the hacker that came up and created John the Ripper, it's extremely fast, but what I really like about it is it works against both Unix and Windows passwords. Here's a diagram showing you of an example of John the Ripper running on Unix and Linux. As you see this John --test, this says in John the Ripper, I'm going to test for this hardware how fast I can crack passwords. As you start looking down through there, you see the different salts and seeds, but the area highlighted in the box is OpenBSD Blowfish. Look at how many crypts, the C stands for crypts. How many crypts per second can he do against OpenBSD Blowfish? 400 crypts per second. Let's take another example, NTLM, which is the bottom one. It says 7710. There's a K next to that, folks. That means that 7.7 million crypts per second, he can do landman hash cracking. But OpenBSD, he can only do 400. This is why in a secure environment, a lot of organizations might deploy BSD. If in your red team hacking, you run into an OpenBSD box, good luck. They're very difficult to crack. But the good news is they're written by and created and configured by humans. So the human can make a configuration mistake, so you always gotta try. Part of a red team is if we identify it as what we call a hard target, we document it, we move on, it's a hard target. If we get time, maybe we'll go back and look at it later. Sometimes you're looking at hundreds, thousands of targets, and you just do not have time to look at everything on every target. You look for the easy, weak targets first, and then come back for the hard targets later. We call it prioritization in testing. Here's a John the Ripper in Windows. We can customize John the Ripper, and here we got an example showing you of a john.ini file, which is in Windows, and you can specify a range of characters. This is really good if you know an organization has a policy because they post it all over their public information that says your password must be 8 characters or greater. That means with John the Ripper, we can go in and tell it, don't even start with words less than 8 characters. Start at 8 characters and above because we know that's what's being used. So when we go into brute force, we'll brute force from 8 characters and above. Here we'll break, and I'll do a demo of John the Ripper.